Okay, we're now in section 15.8, electric flux and Gauss's law. Okay. Gauss's law is a technique for calculating the average electric field on a closed surface. It was developed by Carl Friedrich Gauss, who lived from 1777 to 1855. Gauss's law relates the electric flux through a closed surface and the total charge inside that surface. A closed surface has an inside and an outside. An example is a sphere. Electric flux is a measure of how much the electric field vectors penetrate through a given surface. Let's consider an electric field that is uniform in both magnitude and direction, as in the figure. The electric field lines penetrate a surface of area A, which is perpendicular to the field. The technique used for drawing a figure like this is that the number of lines per unit area, N over A, is proportional to the magnitude of the electric field, which we can rewrite as N is proportional to EA, which means that the number of field lines is proportional to the product of E and A, called the electric flux, represented by phi. Phi is equal to EA. The electric flux is proportional to the number of field lines that pass through some area A oriented perpendicular to the field. We call it flux by analogy with the term flux in fluid flow, which is the volume of liquid through a perpendicular area per second. If the surface is not perpendicular to the field, as in the figure, the expression for the electric flux is shown here, where a vector perpendicular to the area A is at an angle theta with respect to the field. We will refer to this vector as the normal vector to the surface. The number of lines that cross this area is equal to the number that cross the projected area A prime, which is perpendicular to the field. That is when theta equals 0. And that the flux is 0 when the surface is parallel to the field, when theta equals 90. By convention, for a closed surface, the flux lines passing into the interior of the volume are negative, and those passing out of the interior of the volume are positive. This convention is the same as requiring the normal vector of the surface to point outward when computing the flux through a surface. Let's consider a point charge Q surrounded by a spherical surface of radius r, centered on the charge, as in the figure. The magnitude of the electric field everywhere on the surface of the sphere is given in the equation shown. E equals KE r squared. Note that the electric field is perpendicular to the sphere, to the spherical surface at all points on the surface. The electric flux through the surface is simply EA, where A is the surface area of the sphere. It's sometimes convenient to express KE in terms of another constant. The constant epsilon 0 is called the permittivity of free space and has the value shown. 8.85 times 10 to the minus 12 coulomb squared per Newton meter squared. The use of K sub E, or epsilon 0, is strictly a matter of taste. I may use one or the other, depending on the situation. Gauss's law. We can now express electric flux through the closed spherical surface that surrounds the charge Q as shown. This result says that the electric flux through a sphere that surrounds a charge Q is equal to the charge divided by the constant epsilon 0. This result is true for any closed surface that surrounds a charge Q. For example, if the surface surrounding Q is irregular, as in the figure, the flux through that surface is also Q divided by epsilon 0. This leads to the following general result, known as Gauss's law. The electric flux through any closed surface is equal to the net charge inside the surface divided by epsilon 0. So that's key. I'm going to repeat it. The electric flux through any closed surface is equal to the net charge inside the surface divided by epsilon zero. Gauss's law describes how charges create electric fields. In principle, it can always be used to calculate the electric field of a system of charges or a continuous distribution of charge. In practice, the technique is useful only in cases with a high degree of symmetry. For example, spheres, cylinders, or planes. With the symmetry of these special shapes, the charges can be surrounded by an imaginary surface called the Gaussian surface. This imaginary surface is used strictly for mathematical calculation and is not an actual physical surface. Even though Gauss's law in this form can be used to obtain the electric field only for problems with a lot of symmetry, it can always be used to obtain the average electric field on any surface. An important circuit element that we will study in the next topic is the parallel plate capacitor. The device consists of a plate of positive charge with a negative plate placed above it. The sum of these two fields is illustrated in the figure. The result is an electric field with double the magnitude in between two plates. Outside the plates, the electric fields cancel. Okay. That's it for the chapter.